My dear students, today class is optical activity. My name is Balkishan, lecturer in chemistry, Government Degree College, Siddipet. Optical activity. Optical activity. Optical activity. The phenomena of rotation of plane polarized light (PPL) is called optical activity. The phenomena of rotation of plane polarized light is called optical activity. The compound which exhibits optical activity called as optical active compound. Optical active compound. And next one, the compound which does not exhibits optical activity called as optically inactive compound. Optically inactive compound. This one. Optical activity OP and optical activity depends on number one, nature of substituent, nature of substituent, nature of substituent, nature of substituent, or nature of compound, second one, concentration of solution, third one, temperature, fourth one, source of light, fifth one, length of tube. So these are the effective factors. Okay. Optical activity. The phenomena of rotation of plane polarized light is called optical activity, and the compound which exhibit optical activity called as optically active compound, and the compound which does not exhibit optical activity called as optically inactive compound. Optical activity depends on following factors: and the nature of compound, concentration of the solution, temperature, source of light, length of the tube. Now, how to know the compound is optically inactive or optically active? Optical activity can be explained with the help of the following. The compound which satisfies the following the following conditions and the following conditions can exhibit optically activity. Can exhibit optically activity. Number one, first point, must contains at least one chiral carbon. At least one chiral carbon. Must contains at least one chiral carbon. What is chiral carbon? Chiral carbon, the carbon which contains 4 different groups. Here A, B, C, D. These are the 4 different groups. Then this carbon is called as chiral carbon. Then the carbon is called as chiral carbon. Okay. Must contain at least one chiral carbon. That means I am taking example OH, H, CH3 and Cl. Then this carbon is the chiral carbon. That's why it is the optically active. Optically active. Okay, this is the one point. Second point, absent if plane of symmetry absent. If plane of symmetry absent, then it is an optically active compound. Optically active compound. Optically active compound. Optically active compound. This one. If plane of symmetry absent, then it is a optically active component. But what is plane of symmetry? I am taking one example only. This is the COH and this is the COH. In between carbon here OH and carbon OH. This is the tartaric acid, mesotartaric acid. When we assuming a plane, this plane this is the one imaginary plane this plane is dividing the molecule into 2 equal halves two equal halves. Then the plane is called as plane of symmetry. Plane of symmetry. Okay, this is the definition. The imaginary plane which can divide the molecule into 2 equal halves. Two equal halves. The plane is called plane of symmetry. Plane of symmetry. It is denoted by sigma. Plane of symmetry is denoted by sigma. If sigma is present if present, sigma is present it is optically inactive. Okay. Sigma if absent absent, optically active. Optically active. This is in this tartaric molecule, mesotartaric acid, plane of symmetry is present and that's why it's optically inactive. Optically inactive. I am taking another example. Okay, these are the first condition is must contains at least one chiral carbon. So this is the first one, at least one chiral carbon. Second, what is chiral carbon? The carbon which contain 4 different groups is called as chiral carbon. Is called as chiral carbon. Now, this is the example for the chiral carbon. Second point is, if plane of symmetry absent, then it is a optically active component. But what is plane of symmetry? The imaginary plane which divides the molecule into two equal halves. Two equal halves. Two equal halves. The plane is called plane of symmetry. It is denoted by sigma. If sigma present it is optically inactive compound. If sigma is absent it is optically active. Example for the sigma mesotartaric acid. That's why it is optically inactive compound. Okay. You take another example. This is COOH. COOH and carbon. Here also carbon. Here left side is the OH, right side is the OH. Here right side is the hydrogen, here left side is the hydrogen. When we are imagining a plane this plane, these are not the two equal halves. This side is H this side is the OH. That's why these are not two equal halves. This is not equal. That's why this is the optically active compound. Optically active compound. So this is plane of symmetry. Now, third point center of symmetry. Center of symmetry must be absent. These are called symmetry points. Okay. Next to plane of symmetry absent and center of symmetry is also absent. Is absent. But what is center of symmetry? Means I am taking a molecule. This is the molecule. This is the molecule. Here I am writing hydrogen. Here also hydrogen. Here methyl group. Here hydrogen, methyl group. Here hydrogen, hydrogen. Here hydrogen, hydrogen. Here hydrogen, here CH3. Okay, here CH3, here hydrogen. This is one example. I am assuming this point. Assuming this point from top to this bottom I am extending a line to this center point and the distance from center point Iiyr to Iiyr and the if same. Now here also one more, upside is the hydrogen, downside is also hydrogen. Same atom, that line is touching through a center point and the distance between the center point to hydrogen and this center point to this hydrogen is same and the distance between from here hydrogen and to the center point from here hydrogen is same and this is CH3 and I am extending a line up to center point. Here also CH3 and H. So this line also touches this group only with same distance. A imaginary point which can touch similar groups with same distance only in a molecule, then the imaginary point is called as center of symmetry. It is denoted by I. It is denoted by I and okay. If this molecule is optically inactive due to the presence of center of symmetry and okay, this is the center of. Now next point and the axis of symmetry. Axis of symmetry. Axis of symmetry. This is the some axis and I am taking one example. This is the carbon, another carbon, this one. Okay, I am writing here CH3, here CH3, here Cl, here Cl, here H, here H. This is the one molecule. When this molecule and rotated by with this one and okay, I am just showing the axis and now this is upside is the CH3 and this upside is the CH3. Okay, now I am taking this an imaginary axis and which is rotated by some angle and some angle means and this is axis. When it is come to the top and 90 degrees, when again it down the 180 degrees, so this is the 270 degrees, when same place is the 360 degrees. Okay, when this is the black color clip is I am saying as a CH3 and this CH3 is the upside and this CH3 is the upside. So this is the imaginary axis and along this imaginary axis, when this molecule is rotated by 180 degrees and so this is the rotation by 180 degrees. What happened? This is the imaginary axis and just it is shifted from here to this one and the obtained molecule structure is this one. Okay, this downside and here Cl, here H. This downside CH3 will come upside. Okay, this one and Cl is same and H is same and this upside CH3 will come to downside, remaining same Cl and H. Okay, You compare this. This is the original first structure. This is second structure. First and second structures are equal. Then this imaginary rotation axis is called as axis of symmetry. This is called as CN axis of symmetry. CN axis of symmetry. Okay, simple axis of symmetry and common axis of symmetry. Okay, that definition and if a molecule rotated by 360 degrees by n and n may be integer 1 2 3 dash dash, n may be integer 1 2 3 dash dash. If it is 1 and 360 degrees, all molecules will give. If it is 2 and 180 degrees, I have rotated this 180 and 360 degrees by n and that is equal to 180, n is equal to 2 and this is called C2 axis of symmetry. 180 degrees is called as C2 axis of symmetry. Okay, now C2 axis of symmetry is present in this molecule. Why? The definition is if a molecule is rotated by 360 degrees by n angle along a imaginary plane and the obtained image or structure, if similar to the original structure, first structure, then the imaginary axis is called as axis of symmetry. Axis of symmetry or CN axis of symmetry. This molecule is present CN axis of symmetry. Next one is, after this one, alternative axis of symmetry. Alternative axis of symmetry. Alternative axis of symmetry. Here alternative axis of symmetry means only, this is, observe this one. This is the CH3 and this is also CH3. This is the H, Cl and Cl. This is one molecule. Okay, this one I am taking. This is the structure only. The clip is lead CH3 group. And in this molecule, I am taking this is the axis from plane to rotated upside and downside. So this is the, now I am taking here this type of axis. When it is rotated, this one from left side to I am rotating towards the right side. So this is the angle of axis of rotation. This is the axis of rotation. What I obtain and the structure is, new structure is this one. After the 180 degrees rotation, we obtain this structure. That CH3 downside is obtained this side only. So this is the CH3. This is the H only. This is the Cl. Okay, and this is the CH3. This is H. The outside one is the front side only. This is Cl. Front side will go back side only. And here upside is the CH3. And downside is this one, come front side Cl. This is the H. If a mirror is placed at the perpendicular to the rotation axis, we obtain this structure. This is the upside, this one is downside CH3. Okay, this is the Cl, so this is the H, and here CH3, this is the H, this is the Cl. So this is the first structure, this is the second structure after the rotation, this is the third structure. Here first is equal to third. You see, the first structure is equal to third structure. In first structure, CH3 is upside and hydrogen is front side, Cl is back side, and hydrogen is back side, Cl is front side, CH3 is downside. 1 is equal to 3. So based on this one, we can define definition, and if the molecule is rotated by 360 degrees by n angle through an imaginary axis. This is the imaginary axis. This one is imaginary axis. And the obtained structure mirror image. So this is the obtained structure. Mirror image is similar to the original structure. Then the imaginary axis is known as alternative. This first, second, third. Third is the alternative. That's why it is called as alternative axis of symmetry. It is denoted by SN. It is denoted by SN. So these are the symmetry points, and you observe that one here, and to exhibit optical activity, and the following conditions are the important. Number 1, must contains chiral carbon, at least one chiral carbon, Second one, absent, that is sigma, plane of symmetry. Absent I, that is center of symmetry. Absent Cn, absent Sn. So these are called as conditions to exhibit optical activity. This is very, very important. Okay, there is a minimum one chiral carbon, at least one chiral carbon. Chiral carbon means 4 different groups containing carbon, A, B, C, D, and 4 different groups. It's called as chiral carbon. At least one chiral carbon. And plane of symmetry means only when the molecule is divided with alpha of imaginary plane into 2 equal halves, the imaginary plane is called as sigma. Sigma, if absent, it is optically active. And I, center of symmetry. A line is extending from an imaginary point from bottom to upside, from the one side to another side. If it touches 2 equal groups with same distance, then the imaginary point is called as center of symmetry. It is denoted by I. I, if absent, it is optically active. Then if axis of symmetry, C and axis of symmetry, if absent, it is optically active. Absent is optically inactive. Sn is the alternative axis of symmetry. In some cases, it may be active or it may be inactive. That's why, based on this symmetry points, optical isomers are classified into 2 types or 3 types. Optical active compounds are classified into three types. One is the symmetric molecule. Okay, based on symmetry points. Symmetry points here sigma, I, Cn, Sn. These are known as symmetry points. Based on symmetry points based on symmetry points, optical active compounds are classified into three types. One is the symmetric molecule. Symmetric molecule. Symmetric molecule. Second one is disymmetric molecule. Asymmetric molecule. Here very simple symmetric molecule first one symmetric molecule. Symmetric molecule. If a molecule contains all sigma, I, Cn, Sn, all these points are symmetrical point, that is symmetry points. If present it is called a symmetric molecule. It is optically inactive. You take, this is the symmetrical molecule. When it is divided into two equal halves, it divides into two equal halves and a imaginary plane. That plane is called center. That means it contains center of symmetry. Optical, this is not the chiral carbon. No chiral carbon is present. Sigma is present. I also present, and Cn also present. Everyone, all are same groups, and that's why this is called a symmetric molecule. And you take methane also. This is also symmetric molecule. Okay, that's why symmetric molecule is optically inactive. And in symmetric molecule, all sigma I, Sn, Cn are present. After this one, the disymmetric molecule. The second one is disymmetric molecule. Disymmetric molecule. Disymmetric molecule means the molecule which absent sigma, I and Cn but present Sn. Called as disymmetric molecules. Okay. Ade asymmetric molecule తీసుకుంటే all are absent and sigma absent, I absent, Cn absent, Sn absent. All asymmetric molecules are the disymmetric molecules. But all disymmetric molecules are not the asymmetric molecules. So this is about the optical activity. Okay, optical activity, the minimum condition. There is no sigma, there is no I, there is no Cn. In some cases there is absent Sn. That is not the criteria. These are the main: sigma absent, I absent, and Cn absent, and contains a chiral carbon. Then it is the optically active compound. Okay. Now some examples. This is the first example. CH3, CHOH, COH. This is called as lactic acid. In lactic acid, this one is chiral carbon. This one is chiral carbon. And the first point, chiral carbon is present. Is present. is present. This one point. తర్వాత when it divided into two, it is seeing అండి a imaginary plane, it is not dividing two equal halves అండి. This is the imaginary plane అండి. Here CH3, in that one COH. That's why it is not dividing into two equal halves అండి. That's why sigma is absent. Similarly, this is a center point when extended with same distance and here touches CH3, here touches COH. That's why I is absent. I is absent. And the next one, when it is rotated with 360 degrees by n and that may be 90 degrees, that may be 180 degrees, that may be any other degrees and will not obtain same shape. That's why even though Cn is also absent, Sn is also absent. That means it is a asymmetric molecule. Asymmetric molecule. It is a asymmetric molecule. Okay, this one. Okay, and one more important formula. If in a molecule n chiral carbons are present, n chiral carbons are present, then number of optical isomers is equal to 2 to the power of n. In this case only one chiral carbon is present. In this example only, in lactic acid one chiral carbon is present. That is n is equal to 1. Therefore, number of optical isomers is equal to 2 to the power of n. 2 to the power of 1 is equal to 1. Based on this one only, these two are, we can write this one only, CH3, COOH, and one OH is right side. In second type of one only, OH is left side. So these are the two isomers. In that one is the dextroisomer, other one is the levoisomer. Okay, so this is one example. One more example I am taking. Similar one only. Second example, CH3, CHOH, CH1. It is called as glycerol-Iiyr. Okay, CH2OH, CHOH, CHO, called as glycerol-Iiyr. In this glycerol-Iiyr, this is the chiral carbon. This carbon contains HOH, CHO, CH2OH, 4 different groups. That's why it's called as chiral carbon. One chiral carbon is present. First point is satisfied. Second point, sigma absent. Third point, I absent. Fourth point, Cn absent, Sn also absent. That's why it's optically active. Okay, and it exhibits 2 to the power of n. Here chiral carbon is equal to 1. There is two isomers. Optical isomers is equal to 2. Optical isomers number of optical isomers equal to 2. In that one, this is the similar structure only. Here this one CH2OH, CHO, here CHO, CH2OH. These are the two isomers of the glycerol here. This is the glycerol here. Glycerol here. Okay, that's why glyceraldehyde contains glyceraldehyde contains how many? That is one chiral carbon is present. One chiral carbon is present, and sigma is absent. Sigma is absent. I is absent. Cn is absent. Optically, therefore it is optically active. Okay, one chiral carbon is present, sigma is absent, I is absent, Cn is absent, even though Sn is also absent. And that's why it is optically active. And number of optical isomers is equal to 2 to the power of n formula is equal to 1. In this, this is one isomer, this is the second isomer. In first isomer, OH is the right side. In second isomer, OH is the left side. And this is one is the dextro, other one is the ligand. So this is the optical activity. This is very important for your examinations. Thank you. Today class completed.